Okay, so we are in chapter 10, the last chapter, and we will talk about VSEPR structures and how they look like, planar, tetrahedral, and trigonal planar. And we are going today to talk about hybridization, okay? Before we start that, I think there was a homework. Also, we talked about polarity, if molecules are polar or not. What else? Okay, we talked about the valence bond theory as well. I explained briefly what is the valence bond theory and how does bonds forms, okay, according to this figure. And today we're going to talk about hybridization, which is the last topic of this semester. Now, before we start, there was a homework last time about CH2, CL2, and thanks Dima for sending me the solution for the homework. This is indeed a polar molecule. And how you? Oh no! There was. She just sent me that in the. It wasn't an official homework. She just sent me that in the email. Thanks, Dima, but there was no marks for it anyway. It was just kind of an informal homework. But yeah, thanks for asking. CH2Cl2 is polar, and the way you know that because you need to draw first the lowest structure, and from the lowest structure, of course, you cannot determine polarity. So this is lowest, according to Lewis, it's not polar anyway. But Lewis is wrong. You always have to go to VSEPR. Now, the arrangement of electron pairs around the carbon is 4, so therefore this is tetrahedral, and it looks like this. Maybe something like that, okay? You will learn on organic chemistry how to draw these molecules in a good way. But anyway, tetrahedral. So tetrahedral by itself is non-polar, but what's happening here is that this hydrogen, this carbon is more electronegative than this hydrogen, so this bond is polarized this way. This bond is polarized this way. Chlorine is more electronegative than carbon, so the pull will be this way. You see, everything looks like this molecule. The net dipole moment is to the bottom right, and therefore here mu is not equal to 0 on this indeed polar molecule. Okay, so that's the solution for the homework. Okay, good morning again for the people who joined us. Today we are going to start this lecture with hybridization, and that will be the last official lecture for this semester. Today we're going to have also a class activity that we're going to start at 8:30. So bear with me, understand what I'm saying here in order to solve the class activity. So كل عام وانتم بخير. Tomorrow is Ramadan inshallah. Wish you happy Ramadan inshallah and happy life. And next week we are going only to do only revisions. Okay, only revisions. Right. Now, let's start with hybridization. I'll tell you what's going on here with hybridization. Okay, let's take a simple molecule like CH4, which is methane. Okay. And try to think, what are these bonds between the carbon and the hydrogen are from? So we have C, H, and then another H, another H, another. What is this bond? Call this a sigma bond. What is it exactly? These are two electrons, but how is it formed? What orbitals are making this bond and so on? Well, we'll start with carbon. And carbon, the atomic number of carbon is 6 in the periodic table. So the electronic configuration of carbon is 1s2, 2s2, 2p2. Okay? And therefore, looking at the valence shell of carbon, we don't care about the electrons in the core. Carbon should have a 2s orbital, and there are 2 electrons on it, and they are paired. We have 3 subshells, 2px, and a 2py, and a 2pz, okay? And there are only 2 electrons here, so there is 1, 2. With this situation, I don't understand how carbon will make 4 bonds with hydrogens, because you have 4 hydrogens, let's call them H1, H2, H3, and H4. And this is the first hydrogen, this is the second hydrogen. These are the hydrogens, and each hydrogen has 1 electron on it. In a 1s orbital, right? This is 1s orbital in hydrogen, this is 1s, and so on. So now, if you want to think about it, okay, this electron can bond with this one can bond with this one. But what are these two? These two are paired. Paired electrons, they cannot make bonds. How could they make bonds? They're already paired, okay? So with this, we have a problem making bonds, okay? The problem is twofold. One, we have paired electrons that they cannot make bonds, okay? And number two is that even if they make bonds, we will have a bond between 1s and 2s orbital and a bond between 1s and 2p orbital. And therefore, we're going to have different bonds in CH4. But we know experimentally that these bonds in methane, they are all equal with they're all equal with the same size, with the same bond length and everything. But having a bonds between S and S and S and P and having different bonds doesn't make sense. So this situation is not acceptable, and therefore what's going to happen here is that something magically will happen, and we call it hybridization. So the solution is we go with hybridization, tahjeen, okay? It's like, you know, in the hybrid car, you have now electric motor that works both in electricity and fuel. It's called a hybrid car. What happened here is that one electron from the S, okay, goes here. This one will lead you to the 2s and the 2p. Now the 2s has 1 electron, and this one has the one, and this one has 1. And this electron here will fly there, so it's going to be like that. Now we have 4 orbitals with 4 electrons. Now hydrogen can come in easily. Okay, the 4 hydrogens, I mean, this is 1s, 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 electron, 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 electron. They're gonna make bond S. Now, what are these new orbitals called? This is an orbital that is made by mixing 2s with 2p, right? Now we have here, we have 4 orbitals here. They are the same. They are all. We have 4 orbitals. Each one has 1 electron, okay, and each one is bonded with 1 s electrons. And there is no meaning to have these orbitals with different energies, and therefore they are all equal. And then now we call them what? We are mixing 2s with a 3p, okay. So we're mixing 2s orbital with the 3 orbitals of p, and we mix them together to get to this, and we call this sp3 hybridization. sp3 hybridization, okay? Because we have, so this is sp3, this is sp3, this is sp3, and this is sp3. How does an sp3 orbital look like? An sp3 orbital looks like this, because you are mixing a 2s orbital, okay, with a 2p orbital. This is the shape of the 2p orbital. You're gonna get something like that, okay? This is the sp3 orbital. It looks like that. Has a small sphere and a big sphere. Okay? It's kind of a 2p orbital, but it's kind of polarized. Okay? This is the sp3. So That's all explained here in this PowerPoint, and that's what I'm talking about. The 2s electron goes, and this is the structure. This is the shape of the sp3 orbital. As I told you, it has a small loop and a big loop. Okay, and this is the shape now of the methane. Methane has carbon in the middle. You have sp3 orbital here, sp3 orbital, sp3 orbitals, and each one is bonded with a hydrogen, and therefore we expect any tetrahedral to be sp3 orbital. That's the take-home message from this whole story here. Any tetrahedral structure or any tetrahedral electronic configuration should have sp3 orbital configuration. So that's not only for methane. Anything that has anything that is tetrahedral. Remember that water itself is tetrahedral. The shape is bent, but the arrangement of electron pairs is tetrahedral, right? And therefore, this bond here, this bond is made from an sp3 orbital in oxygen plus a hydrogen with one s orbital, and this bond is the same thing. Now this lone pair is called a lone pair. This lone pair is also sitting in an sp3 orbital, okay? And the same thing for ammonia. So anything that is tetrahedral electronic geometry, it should have sp3 hybridization. So this is for ammonia again, and look at this. Ammonia, nitrogen has 7 electrons, and there was some hybridization, and the lone pair in nitrogen, in ammonia here, it's sitting in sp3 orbital as well. Okay, and the angle is 109 degrees. Now let's go to another to understand hybridization in a better way. Let me take another example for BH3. BH3 will have different type of hybridization. We call it sp2. So boron in the periodic table has 5 electrons. I'm going to explain this to you again. So 1s2, 2s2, 2p1. Okay, that's the electronic configuration for boron. If you're looking at the valence electrons, so we have 2s and 2p, 3p's of course. So this is the 2s, this is 2px again, 2py, 2pz. Okay, this is paired. You have 1 electron in the p's. Now three hydrogens will come in. Okay, one H with 1 s orbital, another H with 1 s orbital, another H. Each one with 1 electron. Right? This is the H, your H's. This is your hydrogens. How would they bond to boron if this is paired? We have the same problem. We have a problem. Okay. The problem is also twofold. One, we have paired electrons. Two, you're going to have unequal bonds. Because if the first hydrogen forms here, okay, we can bond here. Okay, sorry. This hydrogen will bond here, right? What about these two? They will bond there? Well, that's an accident. And even if you do, you'll expect to have unequal bonds because you have an S with P and an S with S. That's not a good solution. And the solution for this whole story is you make hybridization. By having this electron flying here, okay? That will lead you to a situation where you have three orbitals. This one has 1 electron, this one has 1 electron, this one has... There will be a 2pz that is empty in this, okay? So here you are mixing S with 2p's. You're mixing these three, okay? So that's called sp2 hybridization. sp2, and this is sp2. So this is called sp2, it's written as sp square, okay? sp2 hybridization, where the 2pz is an empty orbital and it has different energy and it's sitting by itself. Now the hydrogens will come happily and bond. This one will bond here, this one will bond there, this one will bond here, and you're gonna make your bonds. Okay, the shape. So therefore, you know, boron is boron trihydride is trigonal planar. Okay. So this bond here in boron trihydride is made by an sp2 from boron plus one s orbital from hydrogen. Okay, and there are no lone pairs in boron. You have only 3 sigma bonds. Now, what is the shape of the sp2 orbital? What is the shape of the sp2 orbital? The shape is just like the sp2. The shape of sp2 is that you have a 1s orbital mixing with a p orbital. It's going to make you also small. This is it's a very similar shape. Okay. Now, this is 1s, and this is a 2p orbital, and they are bonding head to head. Like, okay, and that's gonna make you a sigma bond. It's called sigma. This is a strong bond. Okay, we call it sigma. Sometimes you write it like this: sigma bond. Because it's head to head, like because the s orbital comes and forms. There's another type of bonds called side to side. Okay, and that's a pi bond, but it was going to come about it later. But anyways, the s orbital always makes sigma bond. Anyway, that's the rule. Okay, the s orbitals always make sigma bonds, either with s or p or d or whatever. When you're mixing an s orbital with p, with s, or p or d or anything, that's always going to give you a sigma bond, just as a peace of mind here. So we learned about the sp2 hybridization, and we learned about the sp3. There's also sp hybridization, just like the case in beryllium BeCl2. Watch this. Or let's make it simpler by having BeH2. Beryllium has only 4 electrons. So 1s2, 2s2, and therefore, see? Well, how can they are again problem paired electrons? How could that happen? Okay, there's no way that these 2 electrons will bond with the 2 hydrogens because they are paired. So what's happening here? There is an empty 2. This is 1s. This is 2s. There is 2p orbital that is empty right after the 2s. 2px, 2py, 2pz. So this electron will jump here, leading to hybridization, and the hybridization is going to be like this. You're mixing one s orbital with one of the s orbitals, it's 2s, with one of the p, and the 2px and the 2py and 2pz will be empty. So therefore you have a situation like this. You have 2 orbitals, each one has 1 electron each, and this is 2py and 2pz are empty and they are sitting higher in energy. This is called sp hybridization because you're mixing one of the s with one of the p's. And this is called sp hybridization. And now you have beryllium attached to hydrogen, It's a linear molecule, right? Linear. And this bond here is made from a beryllium with the sp orbital plus h with one s orbital. The take-home message is that linear is always what? Linear is always sp. And trigonal planar, we forget to add this here for this one. Trigonal planar, I'm not talking about the shape, I'm talking about the electronic geometry. Planar, like the fan in the ceiling, it's always sp2, okay? And tetrahedral is always sp3. So that's the 3 types of hybridization required at this level. We have they are not summarized somewhere, but you can summarize them. You can summarize them here in this slide, in slide number 51. You have sp3, which is tetrahedral. You can add this to the slide if you like. So here at the top, sp3 tetrahedral. You have sp2, which is planar, trigonal planar. You have sp, which is linear. You have also other types of hybridization, which is sp2d and sp3d2, but that's not included in at this level of chemistry. Okay. So this is anything that is linear is going to be sp, and this is the shape of the sp hybridization in BeCl2. It's just similar to BeH2. Okay, BeH2 and BeCl2 are the same. And we already explained boron trihydride, BH3. BF3 would be the same thing. This is the shape of BF3, trigonal planar, with sp2 hybridization. Okay. Okay. Yeah, this is the table I've been talking about. So sp is linear, sp2 is trigonal planar, sp3 is tetrahedral. So any tetrahedral structure like ammonia, methane, water, NH4 plus. If you draw an NH4 plus, it's going to be tetrahedral as well, and that will be sp3 hybridization, of course, on the central atom. Okay, and this is another summary of this type. So I think this question also we don't have to do it because we did already the BH2. PF3 would be just like ammonia. Okay. So that's self-explanatory. So let's talk about double bonds. Now, there's a molecule that is called ethene, CH2. This is not ethene. This is not ethane. This is ethene. Okay, or ethylene they call it. Common name is ethylene or ethene. What is the bond? What is the bonds here? If you draw the Lewis structure of this structure contains a double bond between the two carbons. You can try to draw the Lewis structure yourself, and you will end up with a double bond between the carbons. Now the question is, this is Lewis, right? Now in terms of VSEPR, this carbon has 3 groups. The arrangement of electron pairs in other words, the electronic geometry around this carbon is a 3. And that will lead you to be, this one is actually trigonal planar, because we learned that anything that has a 3 should be trigonal planar with 120 degrees angle, okay? And the same thing for the other carbon. And therefore, the VSEPR structure of this should have 120 degree angle So this is 120 degree, and this equal to that, and is equal to that. They are all 120 degrees, and this is a non-polar molecule. This is a beautiful molecule that is non-polar. I think we talked about this last time when we had cis and trans dichloro, but this is all hydrogens. It's non-polar molecule. My question is, what is this bond? And what is this bond? What are these bonds made of? Are they SS, SP, SP2, SP3? What are they? Will we know beforehand this is a trigonal planar, and therefore, according to the table that we just finished, this should be SP2, right? But how is it SP2 on carbon? And how does it look like? Let's start as we did before for methane and the other ones. Let's start with carbon. Carbon has always 6 electrons in the atomic number. So it's 1s2, 2s2, 2p2, and therefore you're looking at the valence shell. You have a 2s orbital that has 2 electrons, and you have a 2px, 2py, 2pz. Only the first 2 are occupied. Okay, this is unhealthy situation for making bonds with hydrogen, because again the problem of paired and accorded. So in this case, what's going to happen? We have an electron that will travel from here to there. Okay, so we need hybridization, of course. Just assume that hybridization happens all the time. So you will end up with 3 orbitals, where is call them sp2, sp2, sp2. This one has 1 electron, 1 electron, 1 electron. I have here a 2pz orbital that has 1 electron by itself. Now the other carbon is called, this is carbon 1, okay? It's called this carbon 1. Carbon 2, the other carbon, will have the same exact thing happening. So this is carbon, carbon, carbon. So carbon 2 has also sp2, sp2, sp2. Okay, and a 2pz orbital that has 1 electron empty. So what's happening here? This carbon, this electron is busy with the first hydrogen, with one of the hydrogens making bond. This electron is busy with making bond with the other. Remember, there are hydrogens in the molecule. This is 1, 2. And this electron is busy with making a bond with the H. This one is H. These electrons, they're going to make you the sigma bond, sp2, sp2. But you have here 2 electrons sitting in a 2pz orbital. So here first, you have the first carbon and the other carbon. This is making a bond with H. Okay, so this one has 3 sp2 orbitals, and they are 120 degrees. Okay, I should have make them like that. But for the sake of speed, the actual structure of the sp2 is like this, okay? But let me just draw it like that. Now here I have hydrogen with 1 s, and hydrogen with 1 s, and hydrogen with 1 s, hydrogen with 1 s. This is 1 s, this is 1 s, this is 1 s. There is a big, of course, a better picture is shown in the book, but I'm trying here to. This is sp2, sp2. They're making your sigma bond. There is a p orbital, and you know the p orbital, the pz orbital is actually it's perpendicular to the plane of the. So this is a pz orbital here that has 1 electron. There's a pz orbital here has 1 electron. Now the question is this electron in the upper loop or the lower loop? Of course, we answered this question in chapter 7. This electron here in the top. Is it in the bottom or top? Of course, we cannot ask this question. The electron can go anywhere it likes, okay? And we explained the notion of the electron in the chapter 7, and it's delocalized, okay? It's everywhere. So this 2pz orbital now, it's making the bond I told you about, the side bond. So now you have some kind of interaction between, because there is electron in these orbitals at the bottom and at the top, okay? It's like you are having the CC single bond in the middle, but you have some electronic cloud in the top and the bottom, okay? This is called the pi bond. 1 electron, so I'm going to draw this here again. So this is a 2pz, 2pz. There is 1 electron here, 1 electron here, and this is going to make you the pi bond, okay? Pi bond, because it's a side to side. It's not as strong as the sigma bond. It's a weak bond, okay? And we could, of course, and we express this when we write the molecule. We write carbon, sigma bond, carbon, but we add another dash for the pi bond. So the black one is the sigma, and the blue one is the pi, okay? And we draw 1 dash for the pi because there are 2 electrons. Remember, 2 electrons equals 1 bond, okay? So this sigma bond here between the C is made between the sp2, sp2, Okay, and this is a strong bond. But this bi bond is between the 2p, 2p, 2pz, 2pz. Okay. So this is all explained here in the sp2 hybridization in carbon. As I said, we are starting with the regular electronic configuration of carbon, of carbon, which is 2s and 2p. And we have the formation of electrons or transfer. Now you have three sp2 orbitals, okay, but you're having 2pz orbital with one electron left, and this is exactly what's happening. See here at the bottom left, you have the sigma frame, we call it. This is a carbon with a 3 sp2. They are all busy making sigma bonds, but you have also a pz orbital, okay, a 2pz orbital perpendicular to the frame. So it's if you writing this on a plane of the paper, the pz will be actually perpendicular to the paper, and that's going to make you the pi bond at the top and the bottom. This is another picture of it. This is the sigma frame sitting perpendicular to the paper. Now I flip it 90 degrees, so now my C and H's are sitting perpendicular to the plane, and the pi system is on the plane of the paper. Okay, that's the CH2. So that's about it. Now what we have here. So you have one more, which is the hybridization in acetylene. Okay, C2H2 now. It's not C2H4, it's C2H2. Let's do this again. Carbon has 2s2p promotion. Now you have sp hybridization because it's linear, and a 2pz and a 2px orbitals are having one electron each. So this is acetylene C2H2. You have only two hydrogens, so this one of the hydrogens will connect to the carbon. Another hydrogen will connect to the carbon. Okay, and because it's linear, so it's sp hybridization. But you have two p orbitals that are having one electron each, 2py and a 2pz, and therefore you have two pi bonds. Maybe this picture is okay. So you have the carbon, everything in blue here is the sigma, but you have the two pi bonds, okay, two pi bonds. The first pi bond is made of the 2py, 2py, and the other one is between a 2p, 2pz, 2pz. So for acetylene, which is C2H2, you have carbon making a sigma bond with the other carbon, and this is also a sigma bond. So everything in black here is sigma. Okay, this is sigma bond that is made between sigma bond between carbon with sp2 plus carbon with sp, not sp2, because this is linear. Okay, sp plus carbon sp. This bond in black, it's made between C with sp plus hydrogen with one s. Hydrogen has only one s. But here we have also, let's zoom in, we have two pi bonds. Okay, let's draw this one in blue and one in red. These pi bonds now, they are for the 2py and 2p, so they are between the p orbitals in the carbon. Okay. At this point, you can start your Blackboard class activity. You can answer some of the questions, if you can, while we are continuing discussing the hybridization in organic molecules. So if you go to Blackboard in Chemistry 101, you go to assignments. You have till 10 o'clock to finish. You go all the way down, class assignment Ismail. Go to the fourth one, please. Ismail assignment number 4. You can start this assignment and answer the questions that are here. You can answer any question that you can feel comfortable while I'm continuing my class here. Okay, let's solve this question. Describe the bonding in formaldehyde molecule whose Lewis structure is this. Okay, that's a very easy question if you understand. You have a carbon here, you have H, and you have oxygen with a double bond with 2 lone pairs. Now, first of all, this carbon is trigonal planar. Because it's clearly have 3 groups. 1, 2, 3. A double bond counts as 1, okay? A double bond lone pair counts as 1. That's what VSEPR says. In VSEPR structure, lone pair, single bond, double bond, triple bond, they all count as 1, okay? So this is trigonal planar because there are 3 here, and therefore the angle here is 120 degrees. And what hybridization is here? So carbon, the carbon has, any guesses, guys? And the carbon, I don't see your chat window is open, just a second. Yeah, at 9, sir, not at 10. Any guesses on the carbon? What is the hybridization? Anybody can answer in the chat window? I go on a plan. Any guesses? Anybody wants to answer this question on the chat window? Why? What is the hybridization in carbon if it's trigonal planar? sp2. Yes, you're right. sp2. Now let's move on to the oxygen. Oxygen has also 3 groups. You have 1 double bond, you have 1 lone pair, 2 lone pairs. Okay? So this is also a trigonal planar hybridization. And therefore, the oxygen is also sp2. That means this lone pair is actually sitting in an sp2 hybridization. Okay? I know in school or some other places or some other books, they teach you that terminal atoms has no hybridization. Okay, but the matter of the fact is, for us, we consider there is lone pair here and lone pair here. We consider this lone pair to be sitting in an sp2 orbital, not a p orbital. Okay, and this is very important. And therefore, here you have 2 bonds. You have a sigma bond that is made between carbon sp2 plus oxygen sp2, okay? And we have also a pi bond. The pi bond is between the carbon and oxygen, but the pi bond is always between a p orbital, so this is a 2p orbital and a 2p orbital. The 2p orbital is maybe here somewhere, okay? It has 1 electron, and it's making the bond just like in the carbon double bond. Okay, but the lone pair is sitting in sp2 orbital. So now I wish that you understand this situation. So this is actually the solution for this problem. This is very important that you understand it. Watch this. This is the molecule again, carbon making a sigma bond with the hydrogen, and it's making a sigma bond with the oxygen through sigma here in the middle, through sp2 orbitals. But the oxygen has also sp2. One of the sp2 is making a sigma bond with the carbon, and the other sp2 there is a lone pair on it, but there is also a pi bond sitting here. So in the last slide in this chapter, there is a mistake actually. So if you go back to slide 78, there is a mistake that we need to correct. And this here is making, so for this one, the carbon is making a sigma bond with the first hydrogen sp2 with 1 HS, that's right. and this one is carbon sp2 with the other hydrogen okay. But this one now the sigma bond between the carbon and O2 is between CsP2 and OsP2, not 2p, and that's a mistake here. The sigma bond is between carbon sp2 and oxygen sp2, and the pi bond, of course, is between 2p and 2p. And the same mistake here as well for this other molecule. This is not formaldehyde, this is acetic acid, sorry, formic acid. In formic acid, the sigma bond between the carbon and oxygen is also between CsP2 and oxygen sp2, not 2p. So these are two typos here. Please fix them in your slide. This one sp2 and this one sp2 instead of 2p. So please make that clear for you. By this, alhamdulillah, I finished this chapter, and there's something about the molecular orbital theory. Maybe next week we're gonna talk about it a little bit. Okay. Yeah. And next week, inshallah, it will be